Now let's discuss the hardware in a little more detail than before. So here's a nice geographical picture of the hardware. Starting on the West Coast, we have UCSD. This red link implies a dedicated private network. We have a core router in Chicago, which has a network impairment device, although I must admit we've had essentially no use of the network impairment device on the distributed system, and so it's tended to be used in dedicated mode to introduce faults, say, between CPUs and disks and things like that. It was slightly surprising there were not more people wanting to do that. The core router, of course, links to Internet 2 and Exceed. It says TeraGrid here, but that's a euphemism for Exceed. And then we, of course, can cross to the other continents, Europe, and of course China, etc., Asia rather. And JOMS is the European network. TAC has a purple line saying that that's a public link. We could not afford a private link to TAC. There's a machine called Alamo there, Sierra and Lima here. Florida has Foxtrot with a private network only at 1 gigabit. The other one's at 10 gigabits. We have here Indiana University with its collaboration with Purdue, and we have Chicago with the hotel system in Chicago, University of Chicago. And this particular list here is actually given in more detail on the next slide, which summarizes the systems that are available. So here we have the systems. We have, starting at the top, we have the IBM iDataplex, the largest system with 1024 cores, 256 CPUs. That's the machine in India. We just upgraded its secondary storage, so it has 2 terabytes per CPU. One of the things we found from the early purchases, we did not put enough disk on each node because with all these different usages we give the nodes, we need plenty of disk space to support that. Plus, some people, when they do Hadoop and things like that, really need plenty of disks. Then the next machine in size is Anima, 192 CPUs, 768 cores. That's a Dell cluster, that's the Texas. Then we have Hotel, Sierra, and Foxtrot. Those are IBM iDataplexes at Chicago, San Diego, and Florida, respectively. We have a Cray, small Cray XT5M at Indiana University with a significant number of CPUs. Since they now have the cluster mode of running, it's actually found more use because it doesn't have to be used in purely Cray mode. Then we have at the bottom here, we have 4 essentially specialized systems. Bravo, Delta, and Echo are at Indiana University. They each have 12 terabytes of disk per node, and they also have substantial memory per node. And the largest amount of memory, in fact, is Echo, which has it has 292 gigabytes per CPU. Bravo and Delta have half that, 192 gigabytes per 2 CPU node. Whereas, as we see, Echo is 384 gigabytes of memory per node, and that allows it to offer around 5 terabytes of memory in shared memory mode using Scale MP. Delta is special in that it has GPUs as well. So Delta is large memory, GPUs, large disk. Bravo is large memory, large disk. Echo is large memory, large disk, distributed shared memory. And Lima at San Diego is a solid state disk system. Here's just pictures of them. It shows all the systems we have. As you see, the fact I can put them all on one page says they can't be very big. And they all look like modern computer systems. Here's a discussion of the storage. The largest storage system, so-called Xanadu system, is at Indiana University with 180 terabytes. And then all the other sites have storage hardware, um, um, typically operated by some variant of network file system available to users. There's also backup storage at Indiana University for archival use. As well as the storage, of course, another key feature of the system is the support. We have a Drupal portal with the usual functionality. That's where you log into the portal, you get your projects, or possibly you can also get now projects through the Exceed portal. We have a ticket system for help. We have a relatively small user-facing support staff and system admin group. We have a small outreach group, and we have a very strong system admin collaboration with the software group. Now we come to discussing some of the projects. We gave several in the overview. We will not repeat those here. The first example project is largely with Chicago using Nimbus, and it's the important ATLAS particle physics experiment, which runs at the Large Hadron Collider in CERN, and they've been experimenting with FutureGrid and also machines in Canada to explore cloud computing for a Large Hadron Collider experimental data analysis. And you can see here we use this Condor, a workload management system, and a cloud scheduler. And the Condor actually manages the virtual machines. All right, so this slide gives a little more detail on the ATLAS use of FutureGrid. Here's the number of completed jobs from March of 2012 to October 2012. And here's it's a daily plot. You can see it's up to over 6,000 per day in August. Here is the average number of slots used over the same time period, number of simultaneously running jobs. Well, each of them takes one core. These are not parallel jobs. And the overall efficiency is around 42%. So that last remark suggests the importance of improving IaaS infrastructure as a service utilization. That's another one of the projects on FutureGrid. This is not part of the Atlas one. The Atlas one just illustrated why you might need to do that. And here's a typical trace from an ANL Argonne cluster, which is used to motivate this work. And to try to get good utilization of infrastructure, this particular research project, Marshall, Keiki, and Freeman, looked at preemptible virtual machine instances, which allowed you to run, and then if an urgent interactive job came through, you could preempt the running job. And then you had various management strategies for this contention, which was the object of the research. So here's an indication of what happens if you do disable the preemption. You get a utilization of around 40%. That was actually what Atlas saw. Then with preemption enabled, you're allowed to get an average utilization of about 84%. All right, now we come to a different FutureGrid project on investigating the SSD disks on Lemur. In fact, this is details of actually something which was reported in overview fashion in the overview MOOC that we had. So if you look at Lemur, it's a small cluster, only got 8 nodes and 128 cores. but it does have solid-state disk, 480 gigabytes on each node. And this initial study compared the solid-state disk and the traditional hard disk on the node on the Hadoop distributed file system, HDFS, and it plots the relative performance of the two types of disk as a function of the file size in HDFS. So it's clear that, not surprisingly, SSDs do lead to significant performance improvement in this case, which is clearly quite important. Here's another project, the Ocean Observatory Initiative, and that's been worked with the Nimbus group, and they're actually building what you might call dedicated science clouds using Nimbus technology. That's the regional Nimbus clouds, and then they go to commercial clouds, essentially in cloud busting fashion. So this case here is an important case because it's an example of sensors. Ocean observatories are a large number of sensors, and sensors are very suitable to clouds because clouds are what you need for erratic data, and sensors tend to give you erratic data. Sometimes they can give a lot of data, sometimes almost none, and you can instantiate the cloud support on demand for your sensors. So sensors and clouds are a very important set of activities where that is actually going on, actually outside FutureGrid in different cases, although FutureGrid has had other sensor cloud research support.